You have done this without knowing what you were doing. At some point, after a long meeting, after hours at a screen, after a conversation that left you drained, you pressed the heels of your palms against your closed eyes and held them there. Not because anyone told you to, not because you learned it from a book or a class or a video. Your body performed the gesture the way it yawns or stretches, an action that felt necessary before any conscious decision to perform it, a behavior that preceded its own explanation by decades. Pressure felt right. The darkness felt right. The warmth of your own hands against your eyelids felt right. You held the position for a few seconds, maybe longer, and when you pulled your hands away, something had shifted. The tension behind your eyes had eased. The visual noise had quieted. The persistent flicker of screen light that had been imprinted on the retina had faded into stillness. The world looked slightly different for a moment, sharper or softer or simply reset in a way you could feel but not describe. You assumed it was rest. Your eyes were tired. You gave them a break. The gesture was so simple and so obvious that it did not seem to require an explanation. You closed your eyes, pressed your hands against them, and things felt better. Except what happened during those seconds was not rest. 3 distinct physiological mechanisms activated simultaneously, triggered not by any single input, but by their convergence at the same tissue, through branches of a single cranial nerve at one moment. The gesture your body chose was the only configuration that delivers all 3 inputs simultaneously. Closing the eyes alone leaves residual light reaching the retina. Pressing without cupping leaves gaps for photons, and warming without pressure misses the ocular cardiac pathway entirely. Only palming combines pressure, darkness, and warmth to the most densely innervated tissue on the body through the fastest conducting cranial nerve. And the convergence of those inputs, why they amplify each other rather than merely adding together, and why the amplification matters more after 55 than at any earlier age, is the physics the second half reaches after establishing what each input does alone. When your palms press gently against your closed eyelids, the pressure transmits through the eyelid tissue to the globe of the eye itself. Even gentle pressure, the kind that feels soothing rather than uncomfortable, the weight of the palm resting on the bony orbital rim rather than pushing into the eye, slightly increases intraocular pressure and deforms the globe by a fraction of a millimeter. This deformation is tiny, far less than the deformation produced by rubbing the eyes vigorously, but it is sufficient to activate the mechanoreceptors embedded in the sclera and the ciliary body. These receptors are stretch-sensitive ion channels that open when the tissue around them deforms, generating action potentials proportional to the magnitude and duration of the stretch. The sustained, gentle deformation from palming produces a sustained, low-level firing pattern, not the brief burst that a poke or a rub would generate, but a continuous tonic signal that persists for as long as the pressure is maintained. Action potentials travel through the ophthalmic branch of the trigeminal nerve, cranial nerve 5, division 1, the nerve that carries sensation from the forehead, the upper eyelid, and the cornea. The trigeminal is the largest cranial nerve and the fastest conducting sensory nerve in the head. Its thickly myelinated A-beta fibers carry the pressure signal from the scleral mechanoreceptors to the trigeminal nucleus in the brainstem within milliseconds of the deformation occurring. The speed matters. The reflex arc from eyeball to heart completes in under 2 seconds, which is why the cardiac response begins almost immediately when the palms make contact. At the trigeminal nucleus, the afferent signal crosses a single synapse to the motor nucleus of the vagus nerve, cranial nerve 10, the primary cable of the parasympathetic nervous system. The vagus sends an efferent signal down its cardiac branch to the sinoatrial node, the cluster of specialized pacemaker cells in the right atrium that sets the resting heart rate by generating the electrical impulse that initiates each heartbeat. The vagal efferent releases acetylcholine at the sinoatrial node, which slows the rate of depolarization in the pacemaker cells and lengthens the interval between heartbeats. Heart rate decreases. This is the oculocardiac reflex, one of the oldest reflexes in the autonomic nervous system, present in every vertebrate species ever tested from fish to mammals, a hardwired connection between mechanical pressure on the eyeball and slowing of the heart that predates conscious thought, language, and every learned behavior you have ever acquired. Magnitude is not subtle. Gentle, sustained pressure on both eyes through closed lids produces a measurable bradycardia of 10 to 20% within 15 seconds, as Blanc documented in the Canadian Journal of Anesthesia, reviewing the anatomy, mechanism, and clinical significance of the oculocardiac reflex across decades of ophthalmic surgical literature. For a person with a resting heart rate of 72 beats per minute, that is a drop of 7 to 14 beats per minute from a gesture requiring nothing but the palms of your own hands. The reflex is so reliable that ophthalmic surgeons must monitor for it during every eye surgery. Manipulation of the extraocular muscles during strabismus correction can trigger profound bradycardia through the identical trigeminovagal pathway, and surgical teams maintain atropine on standby to reverse a reflex that the patient's body executes without permission. In the surgical theater, the oculocardiac reflex is a hazard requiring constant vigilance. In the palming gesture, it is the fastest non-pharmacological heart rate reduction available through a voluntary action, faster than any technique you can learn, faster than any supplement you can take, faster than any device you can purchase, faster than slow breathing, which requires minutes of sustained respiratory sinus arrhythmia to accumulate a measurable shift in heart rate, faster than cold water on the face. The cold face discussion covered the trigeminovagal activation through thermal stimulation of the first and second divisions of the trigeminal nerve, but the cold face reflex requires access to cold water and activates through a different receptor population, the cold-sensitive TRPM8 channels rather than the pressure-sensitive mechanoreceptors in the sclera. The two reflexes share the trigeminovagal pathway, but enter it through different sensory channels and produce slightly different autonomic profiles. Your palms are always available. They are always warm. The mechanoreceptors in the sclera fire within seconds of sustained contact. The evolutionary logic of the oculocardiac reflex, why a hardwired connection between the eyeball and the heart exists at all in a body that otherwise maintains remarkably few direct reflexes between sensory organs and cardiac output, is debated, but one hypothesis notes that pressure on the eyeball in the ancestral environment typically means the face is pressed against something solid and protective, the ground during rest, the warm body of a parent during nursing, the den wall during sleep. In each case, the appropriate cardiac response is deceleration, a shift toward the parasympathetic state that supports rest and recovery. The reflex may be an ancient autonomic signal, preserved across hundreds of millions of years of vertebrate evolution, that sustained contact on the eyes means safety, and safety means the heart can slow. Whatever its evolutionary origin, the trigeminovagal arc from ophthalmic nerve through brainstem to vagal efferent fires reliably, rapidly, and without requiring any conscious intention or learned technique. You do not need to relax for the reflex to work. You do not need to breathe in any particular pattern. The pressure is the input. The cardiac slowing is the output. The pathway between them is hardwired, and the brainstem executes it automatically. Closing your eyes reduces visual input but does not eliminate it, and the distinction between reduction and elimination is the difference between dimming the lights and turning them off. The eyelids are translucent. Ambient light penetrates through the thin skin of the lid, which is less than a millimeter thick, among the thinnest skin on the body, and reaches the retina in attenuated but measurable form. Depending on the ambient brightness, between 1 and 10% of incident light passes through the closed eyelid, which means the retina is still receiving photons, the photoreceptors are still generating signals, and the visual cortex is still operating in a light processing mode. The posterior cortical regions continue generating beta oscillations, 13 to 30 Hz, the frequency band that characterizes active visual processing, externally directed attention, and the sustained computational work of interpreting incoming visual data. Closing your eyes in a lit room produces dim vision, not darkness, and the visual cortex does not fully transition out of its processing state because the input stream has been reduced, not severed. Cupping the palms over closed eyes creates what closing alone cannot, total photic deprivation. The palm, the fingers, the heel of the hand form a light tight enclosure around the orbit, the warm flesh of the hand sealing against the bony orbital rim, the cupped shape creating an air gap between the palm and the closed eyelid that prevents mechanical compression of the eye while maintaining the light seal. No photon reaches the retina. The visual input drops to absolute zero, not merely reduced, not merely dimmed, but terminated, and the effect on cortical oscillation is immediate, measurable, and categorically distinct from the partial reduction that eyes closed provides. Within 30 seconds of total light elimination, electroencephalography recordings show a pronounced shift in posterior cortical activity from beta oscillations to alpha oscillations, 8 to 13 Hz, the frequency band associated with relaxed wakefulness, internally directed attention, and reduced sensory processing. This alpha dominance, a distinctive rhythm appearing reliably whenever the eyes close and visual input ceases, was among the earliest discoveries in human electroencephalography, as Berger identified in 1929 when he recorded the first human EEG and observed the characteristic low-frequency pattern emerging the moment visual processing stopped. Berger named it the alpha rhythm because it was the first pattern he identified in the electrical activity of the living human brain, and the phenomenon of alpha dominance emerging when visual processing stops has been called the Berger effect ever since. One of the most replicated findings in the entire history of neuroscience, confirmed in every EEG laboratory on every continent in every decade since its initial description nearly a century ago. Well, the shift is faster and more complete with palming than with eyes closed alone because palming eliminates the residual light that keeps the visual cortex partially engaged. Under eyes closed ambient light, beta activity is reduced, but not replaced. The cortex is processing less but still processing. The visual neurons still firing at reduced rates in response to the photons penetrating the translucent eyelid. Under palming darkness, the photon count drops to 0, beta activity collapses, and alpha dominance becomes pronounced within half a minute. The difference is categorical, not gradual. The visual cortex is not dimming smoothly from bright to dark, but switching between two operational states, and the completeness of the darkness determines how fully the switch engages. Metabolically, the implications of this state switch are substantial. The visual cortex consumes approximately 20% of the brain's total energy budget during active beta processing, a disproportionate share for a region that constitutes roughly 12% of total cortical volume. This energy consumption is driven by the sodium-potassium pumps that restore ionic gradients after each action potential, the synaptic vesicle recycling that replenishes neurotransmitter stores after each transmission event, and the glial cell metabolism that supports the neuronal activity throughout the visual processing network. 8 hours of sustained beta processing, 8 hours of screen work, of reading, of visual attention, depletes local glucose and glycogen reserves in the visual cortex, accumulates adenosine and lactate and potassium ions in the extracellular space, and produces the subjective sensation every screen worker recognizes. Eyes that feel heavy, gritty, strained, a visual fatigue that closing the eyes in a lit room does not fully relieve because closing the eyes does not fully stop the processing. 60 seconds of palming darkness triggers the alpha shift that allows the visual cortex to downregulate from its beta state, reduce its metabolic demand by an estimated 30 to 40% compared to active processing, and begin the neural housekeeping. Waste clearance through glymphatic flow, glycogen replenishment in astrocytes, synaptic scaling that restores transmission efficiency, that 8 hours of sustained prevented, pressure and darkness individually, the oculocardiac reflex slowing the heart through the trigeminovagal arc, the alpha shift switching the visual cortex from processing to restoration. The question changes from what each mechanism does alone to what happens when you add the third input, the warmth of the palms against the periorbital skin, and why the three mechanisms arriving simultaneously produce a response greater than any of them can generate independently. The evening I held my palms over my closed eyes with a heart rate monitor on my wrist. 60 seconds, the orbital rim supporting the heels of my hands, the fingers overlapping on the forehead, the darkness complete. My resting heart rate dropped from 71 to 63 within the first 20 seconds and continued falling to 59 by the end of the minute. 12 beats per minute from a gesture I had been performing unconsciously for decades, without understanding that the trigeminovagal arc was firing on every repetition, that the visual cortex was switching states beneath the darkness, that the palms were delivering thermal input to the thinnest skin on the body. Now, the palms of your hands are among the warmest surfaces on your body. Skin temperature at the palm typically ranges from 32 to 35 degrees Celsius, compared to 28 to 32 degrees for the cheeks and forehead. The palms carry this elevated temperature because they contain a high density of arteriovenous anastomosis, direct connections between arterioles and venules that bypass the capillary bed and deliver arterial blood close to the skin surface for thermoregulation. When the warm palms cup over the closed eyes, They create a microclimate of elevated temperature against the periorbital skin, the thinnest skin on the body at approximately 0.5 millimeter, compared to 2 millimeters on the cheek, overlying the orbital vasculature that supplies the retina and optic nerve through the ophthalmic artery. Warmth from the palms activates TRPV3 and TRPV4, warm sensitive ion channels embedded in the periorbital keratinocytes and sensory nerve endings that open at temperatures between 31 and 39 degrees Celsius, as Pyer and colleagues demonstrated in Science in 2002 when they characterized these channels as the molecular transducers of warm temperature sensation. The thermal signal triggers local vasodilation. The arterioles supplying the orbit dilate in response to the TRPV-mediated warmth signal, increasing blood flow to the periorbital tissue. The extraocular muscles that have been maintaining fixation and performing thousands of saccadic eye movements across the working day, and, through the ophthalmic artery, the primary arterial supply to the posterior eye, the retina itself. The increased periorbital blood flow clears the metabolic waste products that accumulated during sustained visual processing throughout the working day. The adenosine that built up as neurons fired continuously, the lactate from anaerobic glycolysis and the overworked extraocular muscle fibers, the extracellular potassium ions that accumulated as millions of action potentials restored their ionic gradients across the retinal tissue. The tired eye sensation that accumulates across the afternoon is partly this metabolic waste buildup, and the relief that palming provides is partly this thermal clearance. Pressure, darkness, and warmth interact through shared autonomic pathways in ways that exceed simple addition. The oculocardiac reflex produces vagal activation. Parasympathetic tone increases systemically. This parasympathetic shift potentiates the alpha dominance in the visual cortex, because parasympathetic autonomic states correlate with and facilitate alpha-dominant cortical patterns. The relaxation of the body reinforces the relaxation of the cortex through bidirectional autonomic cortical coupling. The vagal activation from the pressure amplifies the cortical shift from the darkness through a pathway neither mechanism uses alone. And then, the alpha shift reduces sympathetic arousal globally. The visual cortex downregulating from beta to alpha reduces the total cortical metabolic demand. The brain consuming measurably less glucose and oxygen as its largest sensory processing region steps down from active computation to resting oscillation. The autonomic system reads this reduction in metabolic demand as reduced environmental threat requiring reduced sympathetic vigilance, and it responds by lowering the global sympathetic tone that sustained screen work and sustained cognitive load had elevated throughout the working day. This sympathetic reduction amplifies the bradycardia from the oculocardiac reflex. The heart slows further because both the brainstem reflex and the cortical state change are pushing the autonomic balance in a single parasympathetic direction simultaneously, each mechanism reinforcing the other through bidirectional autonomic coupling. Thermal vasodilation closes the loop from below. Increased periorbital blood flow clears the vasoconstrictive catecholamines. Norepinephrine, epinephrine, that sympathetic activation had deposited in the orbital vasculature during the stressed, screen-focused working day. These catecholamines maintain the orbital vessels in a constricted state that reduces blood flow to the retina and extraocular muscles, the vascular signature of the sympathetic dominance that sustained visual processing and sustains visual processing and sustained stress produce in tandem. Clearing the catecholamines through thermal vasodilation further reduces local sympathetic tone, supporting and extending the parasympathetic shift that the pressure and darkness initiated from above through central autonomic pathways. Each mechanism would produce a measurable effect operating alone. Pressure without darkness would trigger the oculocardiac reflex. Darkness without pressure would trigger the alpha shift. Warmth without either would trigger local vasodilation. But the convergence, pressure, darkness, and warmth arriving simultaneously from one gesture, activating different receptor populations that feed into overlapping brainstem nuclei through branches of the trigeminal nerve, produces a parasympathetic response that exceeds what any single mechanism achieves independently. The pathways do not merely add, they amplify, because each mechanism reduces the sympathetic tone that would otherwise attenuate the other two. When you remove your palms after 60 seconds, the visual cortex, Running in alpha-dominant mode at heightened sensitivity from the brief period of total photic deprivation re-encounters light through a briefly recalibrated processing state. The transition from total darkness to ambient light produces a brief window where incoming photons are processed at higher gain than the normal daytime baseline, the visual cortex applying the slightly elevated sensitivity that the brief deprivation produced through rapid homeostatic adjustment. Colors may appear slightly more vivid for a few seconds. Contrast may seem slightly sharper. The effect is subtle and transient, lasting seconds to minutes rather than hours, but it is the visual cortex processing the world through a briefly recalibrated sensitivity that the darkness and alpha shift produced. This is a 1-minute echo of the cortical amplification. The darkness discussion described across 72 hours. The mechanism is identical. Homeostatic plasticity upregulating sensitivity in response to reduced input. But the magnitude is proportional to the duration. 1 minute produces a subtle visual refresh. 72 hours produces Kluver form constants. The gradient is continuous. LED screens emit light with a spectral peak around 450 nanometers, blue light that is disproportionately stimulating to the melanopsin containing intrinsically photosensitive retinal ganglion cells. These cells are a separate population from the rods and cones that form images. They do not contribute to vision at all. Instead, they project their axons to two non-visual targets: the suprachiasmatic nucleus in the hypothalamus, which is the master circadian clock governing sleep-wake cycling, hormonal rhythms, and metabolic timing, and the olivary protectal nucleus in the midbrain, which controls the pupillary light reflex. 8 hours of screen exposure produces sustained melanopsin activation that maintains a continuous daytime signal to the circadian system, telling the suprachiasmatic nucleus that it is still daylight regardless of the actual time, and keeps the pupillary constriction reflex at elevated activity, maintaining the iris sphincter muscle in a state of sustained contraction that contributes to the end-of-day eye fatigue many screen workers experience. Blink rate compounds the problem. Normal spontaneous blink rate is 15 to 20 blinks per minute, each blink providing a brief interruption of visual input, a momentary darkness that modulates the sustained melanopsin drive. During focus screen work, blink rate drops by 60 to 70%, as Tsuboda and Nakamori published in the New England Journal of Medicine, to as few as 3 to 5 blinks per minute. The sustained melanopsin stimulation becomes nearly continuous. The tear film thins and destabilizes between the infrequent blinks, and the ciliary muscles maintaining near-focus accommodation receive no relief from the unbroken visual demand. Palming delivers total darkness for the full duration, complete cessation of melanopsin stimulation. The circadian signaling pauses. The pupillary system relaxes to its resting diameter as the iris sphincter releases. The ciliary muscles, which have been maintaining sustained contraction to focus the lens at screen distance throughout the working day, release to their resting focal distance at optical infinity because no focal target exists in complete darkness. After 55, the ciliary muscles lose elasticity as the crystalline lens hardens with age. The progressive loss of accommodation, called presbyopia, and sustained near-focus accommodation produces ciliary fatigue substantially faster than in younger eyes because the muscles must work harder to deform a stiffer lens. The palming darkness allows these fatigued muscles to return to their resting state, reducing the cumulative fatigue that produces the end-of-day distance blur, the temporary inability to focus at distance after prolonged near work, that many screen workers over 50 experience daily. That convergence, oculocardiac reflex, alpha shift with photic cessation, and thermal vasodilation, arriving from one gesture held for the full minute, is why I anchored the palming at 3 fixed points in the workday: mid-morning, after lunch, mid-afternoon. Not as rest, as a scheduled parasympathetic intervention using the fastest reflex arc available through a voluntary action, the trigeminovagal pathway from scleral mechanoreceptors to cardiac vagal efferents, firing within seconds, no equipment and no technique. Anyone with a history of retinal detachment, recent eye surgery, or elevated intraocular pressure should consult their ophthalmologist before applying sustained pressure to the globe. The oculocardiac reflex produces bradycardia that is benign in healthy individuals, but may require monitoring in those with pre-existing cardiac conduction abnormalities. When palming is performed with the heels of the hands resting on the cheekbones and the fingers overlapping on the forehead, the cupped shape creates a light, tight seal around both orbits without pressing the palms into the eyeball. The gentle weight of the hands on the bony orbital rim is sufficient. The pressure transmits through the eyelids to the globe, and the scleral mechanoreceptors fire from this indirect contact. The palms rest around the eye, not into it, creating a warm, dark, pressurized enclosure around the orbit. Slow nasal breathing during palming. 5-second inhale, 5-second exhale, layers respiratory vagal stimulation on top of the mechanical vagal input from the trigeminovagal arc. The two vagal inputs stack. The oculocardiac pathway provides reflex-mediated bradycardia, while the slow breathing provides respiratory sinus arrhythmia, and the combined parasympathetic drive exceeds what either input achieves alone. 60 seconds is the minimum effective duration. Removing the palms slowly and keeping the eyes closed for 5 additional seconds before opening them prevents the light shock that rapid re-exposure produces, allows the pupil to readjust, and preserves the brief heightened visual sensitivity the alpha shift generated. Perform 3 times during screen work: mid-morning, after lunch, mid-afternoon. Time to interrupt the sustained visual processing before the metabolic depletion and autonomic shift become entrenched for the remainder of the working day. 60 seconds per session, which is the minimum duration for full activation across the convergent pathways. The oculocardiac reflex fires almost immediately, the alpha shift engages within half a minute, and the thermal vasodilation builds progressively across the full minute as the palm warmth diffuses through the half-millimeter periorbital skin to the orbital vasculature beneath. Shorter than a full minute leaves the thermal mechanism incomplete. Longer than a minute provides diminishing returns. The oculocardiac and alpha shifts reach their peak within the first minute, and the thermal vasodilation plateaus as the periorbital tissue reaches thermal equilibrium with the palms. Total daily investment: 3 minutes distributed across the working day, each session resetting what sustained screen work progressively degrades. The gesture requires nothing beyond itself. The palms are the only equipment required, warm, dark, and pressurized by their own vascular anatomy. The orbital rim is the anatomical cradle. The eyelids are the pressure interface. The reflex arc has been wired and waiting in every brainstem since before the species existed. Now, if you have dry eyes, a condition affecting approximately 30% of adults over 50, the sealed microclimate the cupped palms create prevents tear evaporation during the session. The tear film, which thins and destabilizes during sustained screen fixation because blink rate drops to 3 to 5 blinks per minute, is preserved under the palm seal, protected from the airflow and low humidity of air-conditioned office environments. The warm, humid microclimate encourages the meibomian glands in the eyelid margins to release their lipid secretion, restabilizing the tear film's outer lipid layer and reducing the tear breakup rate when the eyes reopen. The palming does not treat dry eye disease. It provides a minute of the environmental conditions, warmth, darkness, humidity, zero airflow, that the destabilized tear film requires to recover between the sustained fixation episodes that screen work demands. The darkness the palms create is darker than closing your eyes. The pressure they transmit is gentler than rubbing. The warmth they deliver is calibrated by the vascular anatomy of your own hands. The gesture was never rest. It was a 3-system reset the body chose before the mind understood it. The instinct was always the physics. The physics was always the intervention.